Are dry vacuum pumps better than wet vacuum pumps in vacuum applications like freeze drying? It's an age-old question. Well, at least it's a decades-old question. And I've been in the vacuum industry for decades, so I am pretty familiar with the dawn of dry vacuum pumps in the vacuum pump world. So by the end of this video, you are going to know a couple of different dry vacuum pump mechanisms. There are more than we're going to talk about, but that's the ones we'll focus on because they're the most relevant to freeze drying. And we'll also show you the internals and how a rotary vane vacuum pump works so that you have a pretty good idea. And we'll talk about the advantages and disadvantages as well. But you'll know how these pumps work, which is kind of nice. And you'll know why you would want to pick one over the other for freeze drying. If you're new to my channel, welcome. My name is Gene. This is Suntour. I own Suntour, and I answer questions and help people with freeze drying all over the world and with other vacuum applications as well. I've been in the vacuum industries for decades. This is really the strength of my domain. So if you have questions about vacuum equipment or vacuum pumps, how to arrange them, how to maximize your potential, how to minimize your failures and all that sort of stuff, feel free to reach out to me. As usual, I will put my contact information in the links below. You can find me on my website. You can find my phone number. You can find how to contact me via email. Just feel free to reach out to me. I can answer most questions offhand. So let's start with the question, what is a dry vacuum pump and what is a wet vacuum pump? Well, the difference, according to most people, is that wet vacuum pumps are filled with oil and dry vacuum pumps are not. Now, that doesn't mean that dry vacuum pumps have no oil. It means that there is no oil in the area that is wetted by the gases that come from your chamber and go out through the exhaust. That is to say, the actual pumping mechanism that sees the air of the chamber. But it's a rotating piece of equipment, and rotating equipment needs lubrication or it won't rotate for very long. Now, there is one exception to rotating equipment that doesn't actually need lubrication, and I'm sure if any of you out there are in vacuum technology world, you know what I'm talking about. That is the magnetically levitated turbomolecular vacuum pump. Of course, there's no contact there, so lubrication is not necessary. But that's just a little bit of an aside. Okay, so a dry vacuum pump essentially has no oil in the, let's call it the wetted area of the vacuum pump's chamber. Now, why is that important? Well, it's really important because it allows the pump to operate at temperatures that are higher than boiling temperature at normal atmospheric pressure. And it allows it to do it continuously. That is just one advantage. We'll talk about more. Why does that even matter? Well, because when your pump operates at temperatures that are higher than standard boiling temperatures, it means that you will not suffer condensation of water vapor inside your vacuum pump. This is the big problem with oil-filled vacuum pumps. They run too cool. Some of them run fairly hot. Now, you can actually get rotary vane vacuum pumps that are specifically made to run hotter, which allows them to run longer and better in a moisture-heavy application. And guess what? Freeze drying is a moisture-heavy application. But really, dry pumps will outperform wet pumps for many different reasons. So let's talk about some of those reasons now. But before we do that, let's actually just fill in the blanks on what is a wet vacuum pump. When I say an oil-filled vacuum pump, I mean a vacuum pump where the actual sweat volume, that is to say the chamber in the vacuum pump that is exposed to your chamber gases, is actually filled with oil. The oil thrashes around inside that pump at 3,450 RPM for most rotary vane vacuum pumps, for example. And it mixes freely with the gases that come out of your chamber. You will notice sometimes that there's an oil smoke that can come out the exhaust of the vacuum pump. That's not really smoke. It's just very finely divided oil mist right? Because like I said, those things thrash around really fast and it creates a very fine mist. Think of when you put your thumb over the hose and you create a really light mist of water. Same thing, just the particles are smaller. So it's not really burning, but it does create hazards, right? That oil mist that comes out of your exhaust in your pump, that will coat the surfaces in the room, that will coat the surfaces in your lungs and everything else that it touches. For the most part, vacuum pump oil is not really toxic. That doesn't mean that it's sanitary, so be careful with that. Okay, so that's what a wet vacuum pump is. It's a pump that is filled with oil. Are there vacuum pumps that are filled with things other than oil that are wet? Yes, there are actually liquid ring vacuum pumps that are filled with water. And some other types of vacuum pumps that are also filled with other fluids. But for the purposes of freeze drying, we have essentially rotary vane pumps. If you have a big industrial system, you might have a rotary piston pump. This is just a different mechanism that uses sort of a wobbling motion and a piston that orbits around the cylinder rather than rotates inside. But it's the same essential function. It traps pockets of air, moves it from the inlet to the outlet. And the oil that's in a vacuum pump, in an oil-filled vacuum pump, actually acts as a sealing barrier between the compression side of the cycle and the vacuum side, so that you don't have air leak backwards from the high pressure side to the low pressure side, because that will hurt your vacuum performance. In addition to the lack of condensation in a dry vacuum pump, you also have the lack of sticky surfaces inside. This means that most dry vacuum pumps will simply flush through dusts and particulates that are pulled into the inlet of the pump all the way through to the exhaust and flush them out as usually particulates and dust. So really how a dry pump has been set up is that whatever goes into the inlet is what comes out the exhaust. That can be water vapor, that can be even light moisture mists, it can be some particulates, it can be condensables. These things will come out of the vacuum pump at the exhaust. Now, there are some kinds of things that you can pull into a dry vacuum pump that will not necessarily make it to the exhaust. And those are things that are condensable at higher temperatures, like perhaps some oils or other stickies, sugars maybe, for example. And those can actually cause a significant amount of problem in your vacuum pump. So these are things to watch out for. Maybe if you guys are interested, I can make a video in the future on how to best take care of your vacuum equipment if you have dry pumps or wet pumps. Of course, a dry pump doesn't have oil, which means you don't have to change the oil. Some dry pumps are direct drive, meaning that the motor is directly attached to the shaft on the rotor. Some are belt driven. So you need to know that. Belts will need to be changed occasionally. If it's direct drive, you don't even have that burden. There are two different types of dry vacuum pumps that are commonly used in industrial, like commercial size vacuum freeze drying systems. One of those is called the roughing pump, if you will. Usually those are dry screw pumps. And the other one is what's called a mechanical blower or a mechanical booster, a vacuum booster. And those are both types of dry pumps, right? Because you have rotors that are spinning with no contact between them, which means they don't need to have oil or for lubrication or for sealing. Okay, we're going to talk about the two types of dry pumps that you will most likely see in freeze drying. We're going to talk about the dry screw vacuum pump, and we're going to talk about the dry scroll vacuum pump. So a dry screw vacuum pump is a mechanism, or uses a pumping mechanism, where you have two very precisely ground screws that mesh together, and they trap gases that come in the inlet and move it through, compressing along the way and push it out the exhaust. So because it's actually compressing along the way, you get a compression of whatever the vacuum level is that it will establish at the inlet, and you'll have atmospheric pressure here at the exhaust. Now, things of interest in this dry vacuum pump. So as I mentioned before, the bearings, which are on either end, they do require lubrication. If this is a larger industrial dry screw vacuum pump, like a screw line, for example, that you might be using in your freeze drying operation, the bearings will also have timing gears. So the bearings will be oil lubricated and cooled, and there will be timing gears that make sure that these two rotors operate in tandem. So the principle of operation of these vacuum pumps is that these two screws, which are very precisely ground, fit together so tightly that there's just a few thousandths of an inch of clearance between them. They spin quite fast. The outside of this screw is actually sealed against a casing that is shaped to just barely fit the outer profile of these two screws. So whatever gas that's trapped inside these spaces here, even though you can't see the casing here, is trapped inside, and that's why it's forced from the inlet to the outlet. These screws typically spin at anywhere from 5,000 to 7,000 RPM. Some vacuum pumps have them go faster. There are different materials that these dry vacuum pumps can be made out of. Some are made with aluminum. For example, this is the labeled Nova Dry dry screw vacuum pump. The rotors and the stators are all made out of aluminum. I'm pretty sure that they are actually anodized aluminum, so you have a hardened surface. Many of the larger industrial dry vacuum pumps, these rotors are made out of cast iron, as well as the casing. And the only pump that I can think of that is an exception offhand, that's a large industrial vacuum pump that has aluminum rotors, is the Leibold screw line, the SP630. So in wet applications, I have to say that I think that the aluminum rotor is superior, because if you turn off this pump or you lose power and it has a lot of moisture in it, or you take this pump out to do some maintenance on it and you don't properly purge the moisture out, you will have rusting. It will happen very quickly, and it can actually be quite severe. If you send the pump in for repair and it has rust in it, of course, whatever is wrong with the pump will be ignored by the repair company, because they can show that, hey, you have rust in a pump, therefore you damaged it. So an aluminum pump won't rust, right? Because aluminum is exposed to moisture all the time. It's pretty much impervious to rust. Now, that's not necessarily true if you have chemistry inside, so you have to be careful if you are pumping acids and those sorts of things, to make sure that you ask about compatibility before you just go ahead and say, oh geez, I know this pump's going to work, let's buy one. So that's dry screw vacuum pumps. Let's move on to scroll pumps. So a dry scroll pump is a pump that has two spiral shaped stators inside. Well, one is a stator and one is a rotor. Now, these pumps do not spin, they orbit. So they orbit about a camshaft. So imagine that one of these mechanisms wobbles, and I'll put the animation on here in a minute, and you can see how that actually works. It traps a pocket of air in the outer edge, and as it moves through, it pushes this trapped pocket of air from the inlet to the exhaust, which is in the middle. And because the area, the cross-section of the size of the pocket collapses as you move from the outside to the inside, that creates compression, then you get vacuum performance. So here's how it works, right? You trap a pocket of gas at the inlet, like this, and it moves it around the scroll, and you see this scroll is orbiting, it's not spinning. That orbit is what creates the pumping mechanism. Now, scroll pumps were not invented for vacuum applications. They were invented originally for refrigeration compressors. So you will probably have already a scroll pump at your home operating in your air conditioning unit or heat pump, whichever one you have. Almost all small refrigeration compressors are scroll compressors. In fact, the ones in your refrigerator and your freezer are probably also scroll type compressors. The difference between those and these is that those do have oil in, and they're made to operate at pressure, not at vacuum. So why are scroll pumps good and why are they not good? Well, you can see that one of these spirals is wobbling and the other one is stationary. The one that's wobbling is mounted to a plate and the whole plate wobbles. The stationary scroll has to have something that fills the little gap between the plate that holds this wobbling scroll and the fixed scroll. So that little, it's like a little ribbon shaped piece of composite material that's, I think, composite that has graphite and Teflon sort of melded together. That's called a tip seal. It just fits right here in the top of this scroll, and it seals the distance between the scroll, which is the spiral here, and the spiral is usually about 1 inch to 1.5 inches deep. So you have a tip seal on both of these scrolls. One on one side has the plate, and the other one on the other side has the plate. Those tip seals are wear surfaces, right? So why does that matter? Well, it will create dust. So because it will wear over time, you'll have this graphite Teflon composite dust that accumulates in your vacuum pump. The other thing that will happen is you'll have to change those tip seals in order to maintain the low vacuum pressure that the pump will generate when the tip seals are new. So that's one issue. The tip seals will need to be changed on a relatively frequent basis. I think the estimates are maybe up to 6 months of use. It depends on what your process is. The second problem that scroll pumps really have is the wobbling motion. Wobbling motions they're hard on bearings. And the bearings are not, by the way, it's fairly easy to change the tip seals in these scroll pumps. It used to be a real pain in the butt, but it got much better about 20 years ago. So the tip seal, not that much of a problem. You can change them yourself. But if you have to change the bearings because the bearings are wearing out, that is a real problem. And almost no one can do that themselves on site. So you have to send the scroll pump in for repair. And they usually charge you somewhere around $1,700 to do a repair. Now, the third problem with scroll pumps is that for the pumping speed, they are a pretty expensive mechanism. So if you get a pump that is about the same size, let's say 12 cubic meters per hour, which is what the size of the rotary vane pump is you'll find on most boutique size freeze dryers, you're talking about $7,000, $8,000, maybe even $9,000. Now you may say, well, that's more than I paid for my freeze dryer. Yes, it is. It certainly is. And you don't really get the durability because those bearings will wear out in a couple of years. It does not have oil in it, so you don't have to do any oil changes, but it's not really the most durable pump for an application like freeze drying. So I would not recommend the scroll pump for freeze drying applications. Furthermore, if you're doing any kind of commercial freeze drying, it's just not big enough. The biggest scroll pump that I've ever seen you can get is 60 cubic meters per hour, and that's 1/10 of the pumping speed of a screw line, an SP630. Which is standard for commercial freeze dryers. So when would you use a dry screw vacuum pump for freeze drying? You would use a dry screw vacuum pump whenever your freeze dryer is large enough to merit being pumped out with a pump that has that kind of pumping speed. The smallest dry screw vacuum pump that's a reasonable price that I know of pumps at about 65 cubic meters per hour. That's about 40 CFM. So, for example, the TechSource TSS 123 has a dry screw vacuum pump on it, the labeled Nova Dry. If you want to create a central vacuum system to pull vacuum and maintain vacuum on all of your freeze dryers, let's say Like some customers I've spoken to, you have 20, 30, 40, 50 harvest rights or other type small machines, and you want to create a central vacuum system, then a dry screw vacuum pump, you'd need at least 2 of them, would be a really good option, because now the pumping speed is not really it's not over engineered, it's not oversized anymore. So, and by the way, don't just try to do that by yourself. It actually, if you don't do it the right way, you'll pretty much ruin a whole bunch of product, because you need to set up a central vacuum system the right way in order for it to operate correctly for how you're trying to operate. Okay, so that's scroll pumps and screw pumps. Scroll pumps are expensive. They're not really that durable. I really don't recommend them for freeze drying. Screw pumps, dry screw pumps, are really good for freeze dryers that are a little bit larger. I wouldn't use them for any of the boutique size. So what does that leave? That leaves us with rotary vane pumps. Now, a rotary vane pump is a pump with 2 cylinders. 2 cylinders. One is an internal rotating cylinder and the other one is an outer cylinder. You'll notice that the inner rotating cylinder is mostly solid, and it has these vanes that are slotted into it with springs behind them so that they move in and out as this spins. You'll also notice that this inner cylinder is offset on the center of rotation from the outer one, so that the outer tangential rim of the inner cylinder, let's call it the rotor, is very tight tolerances up here between the inlet and the outlet, and creates a gap, a pumping gap, down here on the other end. As it rotates, you will see that it draws air in through the inlet, and it creates an expanding volume, which means it's drawing vacuum. At the same time, it's creating a shrinking volume, which is compression, which will then open this little check valve. Every rotary vane pump has this little check valve at the exhaust. Some have check valves at the inlet as well, but those are not very common. But they all have an exhaust check valve. So as this moves, you'll see that the vanes here slide in and out to maintain a seal around this stator cylinder here. And by doing that, it will trap these gases as it goes. So you can see it happening here. And you'll notice that this valve only opens when you get to a certain level of compression. This is very important. We'll talk about that here on the next video. Okay, I've switched the type of pump that we're going to be talking about now. It's still a rotary vane, but it's now a 2-stage pump. Now, this is just an illustration. 2-stage pumps don't actually have 2 shafts and 2 rotors. 1 stage is actually just attached at the very end here. So you have 1 shaft with 1 rotor, and the rotor has a step down in size. So it'll have a certain diameter, and then it'll have a step down in size of that diameter, so that the gas that's pumped from the 1 stage will exhaust directly into the inlet of the 2nd stage, but it will actually be on 1 rotor. This illustration is just for illustration, although this kind of pump with 2 shafts would actually work in real life if you created one. It would just be wasteful, because you don't want to have two different pumping mechanisms for the same pump. This is a 2-stage pump. Why would you use a 2-stage pump as opposed to a single-stage pump like we saw on the last video? Because when you use 2 levels of compression, you get a much lower inlet pressure. You can get inlet pressures down to single-digit millitors. Okay, so here's again the same pumping principle. You have vanes that are sweeping along, creating an expanding volume and a compressing volume, and it's just sweeping from the 1 stage into the next. Now, it's showing the green molecules here are showing basically air or atmospheric gases, and the little blue molecules in there represent moisture. In a moisture-rich environment like freeze drying, all of the molecules will be water. Now, you'll notice something peculiar, or something that's very important to notice. And that is that as the water compresses, it will create, let's move back here, it will create a puddle of condensed water here at the exhaust. Now, it doesn't just stay in the exhaust, because remember, this pump is filled with oil. It actually mixes with the oil, and as this rotor moves around, it's going to draw a fair amount of that liquid water with it. It's going to start thrashing it around in this oil. If you thrash enough water around in oil, you will create an emulsion, which, if it gets thick enough, is called mayonnaise. And I have seen pumps where some acids were introduced where the oil got as thick as mayonnaise, sometimes thicker even to the consistency of being peanut butter. Normally, if you have a really serious water problem, your oil will simply start to get milky colored. Why is this a problem to have water in your oil? Because it will harm your base pressure. You will no longer be able to pump down to low enough pressures to operate, and it'll also rob you of pumping speed. As these rotors move around and you create the vacuum side, any condensed water will actually flash back into vapor because you've gone below the boiling point again, and that can rob up to a third of the pumping speed of your pump because it's using it for reflashing vapor instead of compressing the air molecules. So as a result, most vacuum pumps will have included in them what's called a gas ballast valve. That will simply introduce air about 2/3 of the way through the pumping cycle. That creates enough gas here at the exhaust to constantly lift that exhaust valve. And what happens when you lift that exhaust valve reliably is it lets the gas out before the water has a chance to condense. So that is why the gas ballast is on your rotary vane vacuum pump, and that's why you should always operate with it open. So when would you use a rotary vane vacuum pump as opposed to a dry pump? When your system is small. There just isn't a good industrial grade, meaning strong, durable, dry vacuum pump that will operate at the kind of small pumping speeds that a small freeze dryer will need. There are small dry pumps that are really good for laboratory, but they're more expensive, right? Again, the small dry vacuum pumps that are, even the ones that are small enough to replace, say, your rotary vane pump, they're more expensive than your whole freeze dryer. So, and they're just not really a great fit. So when you have a small freeze dryer, and that's anything, say, below, if you're going to be putting in anything less than 100 wet pounds of product into your freeze dryer at any given time, my recommendation is that unless you're going to build a central vacuum system where it's all integrated, stick with a rotary vane pump. If you get a good rotary vane pump that operates within the right characteristics, has a really large oil reservoir with automatic water separation, and has the right type of gas ballast, you can actually get quite a good life out of every oil change. If you want to know more information about that, please reach out to me. Again, my contact information is in the description below. I can point you towards a really good vacuum pump that will run for a very long time, give you great performance, and it'll be strong enough to overcome some of those leaks that you're having problems with on your small boutique units. That's just about all that I have for this one. I hope I didn't lose you along the way. This is a very in-depth video, but this is probably as much as you'll find about the difference between wet and dry vacuum pumps as pertains to freeze drying. Again, make sure you keep that gas ballast valve open. The only time that you ever want to close that gas ballast valve is when you're trying to draw very low pressures. And by very low pressures, I mean in the single-digit millitorr. You never will achieve that in your freeze dryer because the ice, the vapor pressure of the ice, when you've got it condensed and it's at minus 25 or minus 40 degrees, is going to have a minimum pressure that it will start to revaporize at 100 millitorr. That's at minus 40 C. It's going to be more like 200 millitorr if it's at minus 25. Okay, so that's it for this time. If you haven't already done so, please hit the like button and share this with your friends if you like.